Welcome back to the video series on the concepts of credit risk. My name is Christian Rumer and I'm one of the co-founders of the company Q-Lana. We continue our explanations with the calculations of the unexpected losses. At least in this video, we will explain to you the concepts of those calculations. Let's pick up where we left in the last video. We have introduced the calculation of expected losses as a product of the probability of default, the loss given default, and the exposure of default. And we have said that the unexpected loss, which we will use as a proxy for the required capital, can be derived from modeling. Let's see how this modeling can work. Remember, in the last video, we had a loan portfolio of 100 loans, homogeneous loans of, on average, $10,000 each. We have calculated scenarios in which 4, 5, or 6 loans defaulted. What happens though if we repeat these scenarios multiple times? And to be specific, what happens if we repeat these calculations 10,000 times? So we build a model which we can actually do in Excel. It's not super complicated. And in this model, we simulate 1 year and calculate the number of defaults in that year. We repeat that exercise 10,000 times and calculate the number of observations. This approach is also referred to as a Monte Carlo simulation, with a reference to gambling to play many times to get a probability. One such scenario or one such modeling you can see on the screen. We used Excel with the data analytics function to prepare the Monte Carlo calculation. As you can see from the histogram, there were 1,768 cases in which 5 loans defaulted. This was also the most frequent observation, which actually should not surprise you. There have been years with no defaults, particularly here there have been 74 out of 10,000 years with no defaults. And there have actually been 4,379 years in which less than 5 loans defaulted. But there have also been 3,853 years in which more than 5 loans defaulted. And there's another observation. The distribution of these losses is not fully normal, but rather skewed, also known as log normal. Because actually in our observations we have seen that there was 1 year in which 17 loans, 12 more than expected, defaulted. Let's see how we can use this distribution and these observations to derive a theory around the estimated unexpected loss. So first, we draw a chart of the distribution, which we have done on the screen. This distribution shows a rather log normal or skewed distribution, because there's only a limited upside, namely situations in which 4, 3, 2, or 1 or no loan defaults. But there is a significant downside because technically up to 100 loans could default each year. The most frequent observation is also the one where we identify the expected loss. If we make the calculation, we can actually see that the expected loss in these scenarios here is approximately $10,000. So no surprise either. And we can define the unexpected loss. To do this, we need to agree on an assumption. The assumption is how safe as a financial institution do we actually want to be? Meaning, in what percentage of the cases do we like to have sufficient capital to cover for the unexpected losses? In other words, the calculation of the unexpected loss is not a finite, fully defined calculation, but it depends really on our desire with regards to our protection levels. Regulators, for example, often use 99% or 99.9% probability for the confidence level. 99.9% means that only in 0.1% of the cases we want to experience a loss that exceeds our capital. 0.1% of the cases for 10,000 observations would be 10. Only in 10 out of 10,000 years, or in 1 year every 1,000 years, would we like to see our institution defaulting. Obviously, allow me to make a side comment, even if we agree that we would like to be safe in 999 out of the 1,000 years, we still don't know when this 1 year will likely be. It could actually be next year. So Let's look at the distribution in a little bit more abstract way. As you can see in the chart, we have the distribution with the expected loss and the 99.9% confidence level. All the losses that accrue up to the expected loss will be covered by reserves. Losses between the expected loss and the 99.9% confidence level will be covered by capital. And only losses in excess of the 99.9% confidence level will lead to default. By the way, the capital does not need to cover the expected losses. The expected losses are actually covered by the reserves. It only needs to cover the unexpected losses. So let's take back our example of our 10,000 observations that we have calculated before and see how they distribute. In the table you see we have added the percentile for each of these categories on the screen. We can see that we had in 1% of our cases, in 1% of the best, or in the best 1% of the cases, we had a loss of $63 per year. And this is calculated with the 1 percentile approach. This includes the many cases in which we had no losses, which, as you probably remember, were 74 in our observations. And there were a few cases in which we lost $2,000 included in the 1% confidence level. So the average result for the 1% confidence level is $63. This means also that we don't have any losses, we don't need any capital, because the $63 are richly covered by the $10,000 of reserves that we have for the expected losses. If we calculate the 50% confidence level or the 50% percentile, our loss is approximately $8,621, so still below the expected loss of $10,000. We still don't have any unexpected loss in those cases. The unexpected loss column therefore shows a 0 value. If we look then at the 90% confidence level, we see that the loss is $14,621 against the expected loss of $10,000. So in 10% of our observations, our losses will be higher, and we have an unexpected loss of at least $4,621. If we raise the confidence level to 95%, we see an increase of the unexpected loss to about $6,000, or to be precise, $6,305. And if we go to the 99.9% confidence level, we see that the unexpected loss will be around $14,019. And if we take it further to the 99.99% of the cases, meaning 1 in 10,000 years, we will see that the loss is $34,000 with an expected loss of $10,000, and we experience an unexpected loss of $24,000. So this table gives us an indication about how much capital should we hold for this portfolio. For a safety level of 99% or 99.9% of the cases, which is, as we mentioned before, often required by the regulators, we would need about $14,000 as equity capital. And if we are more aggressive, we would like to be safe only in 99% of the cases, our capital goes down to $10,153. If you look at these numbers, you can also see that the amount of capital required to go higher in our confidence levels is increasing disproportionately. The difference in equity capital between 95 and 99% is a little less than $4,000, but the increase from 99 to 99.9% is also $4,000. And the increase by another 0.09% costs you $10,000. So, in summary, using model observations and using modeling like a Monte Carlo simulation allows us to derive the required equity capital or the unexpected loss for a portfolio. Remember, in our case, we've only been given a homogeneous portfolio of 100 loans of $10,000 each, and there were a number of simplifications and assumptions that we have done in our model. But the concept is clear, and the concept will not change. This is how you derive the unexpected loss. Now, if you are in a financial institution and if you have the necessary human resource capacity, you can go more sophisticated in the calculation of your risk model. We will go in that direction in the next section, where we'll try to quantify the equity capital needs, not just for a portfolio, but actually for an individual loan. The next section will actually get a little bit more mathematical, but please continue. You are on a good path to complete the training, and I'm looking forward to seeing you in the next video.